This is the third example of combined operations in complex matrices. You are watching numerical solutions to C problems. Given matrix P of 3 by 3 size, the requirement is to determine the notated operations. Have a closer look at the notation. There is adj P, which is the adjugate or adjoint of matrix P, which is involved in the conjugate. This is the bar on top of adj P. Then lastly are the moduli again, which mean determinant. So for the order of operations, the first is to look for the adjugate of the matrix. Then take the conjugate of the adjugate of matrix P, which will be continued into taking the determinant of the conjugate of the adjugate of matrix P. In solving for the adjugate of the matrix, there is a need to look for the cofactor first. So just like the previous examples, identify the minor matrix and take the determinant of each element later. So by covering row 1 and column 1, the minors for element 1, 1 are 1 plus 3i and 5 plus I, with 4 minus 2y and 0. Element 1, 2 has row 1 and column 2 covered, and the minors are 4 minus 3i and 5i, with 4 minus 2i and 0. For element 1, 3, the minors are 4 minus 3i and 5i, with 1 plus 3i and 5 plus I, after covering row 1 and column 3. Moving on to row 2, cover column 1 and have the minors 2 and 5 plus I, with 3 minus I and 0. Right at the middle of the matrix, the minors taken are 3 plus 2y and 5i, with 3 minus I, with 0. And to complete the second row, the minors are 3 plus 2y and 5i, with 2 and 5 plus I. For the third row, start on the left element's minors as 2 and 1 plus 3i, with 3 minus I and 4 minus 2i. Element 3, 2 has minors of 3 plus 2y and 4 minus 3i, with 3 less I and 4 minus 2i. Then the last element to complete the minors matrix is taken by covering the third row and third column, having 3 plus 2y and 4 minus 3i, with 2 and 1 plus 3i. After completing the minors matrix, take the determinants of each 2 by 2 minors to simplify elements. For element 1, 1, the determinant is computed as 1 plus 3i times 0 minus 5 plus I times 4 minus 2i. This is simplified as negative 22 minus 6i. The determinant of the next element in the first row is taken from 4 minus 3i times 0 less 5i times 4 minus 2i. The first term is zeroed out, and you can use FOIL method or just plug in complex numbers in your calculator to have 10 plus 20i. Complete the third element's determinant of the first row by taking 4 minus 3i times 5 plus I minus the quantity of 5i times 1 plus 3i, the result of which is taken as 38 minus 16i. For the row below, start with the first determinant from 2 times 0 minus the product of the binomials 5 plus I and 3 minus I. This is simplified as 16 minus 2I. The determinant of element 2 is solved from the difference of 3 plus 2I times 0 and 5I times 3 minus I. The result is negative 5 minus 15I. For the last element in row 2, the determinant is taken from 3 plus 2I times 5 plus I minus 5I times 2, which is simplified as negative 13 minus 3I. To finish the determinants, element 3(1) is simplified as 2 times 4 minus 2I minus 1 plus 3I times 3 minus I. This gives 2 minus 12I. The next element's determinant is computed as 3 plus 2I times 4 minus 2I. Subtract the anti-diagonal elements product from 4 minus 3I and 3 minus I. The outcome is 7 plus 15I. Then lastly, element 3(3) has a determinant of 3 plus 2I times 1 plus 3I minus 4 minus 3I times 2, giving negative 11 plus 17I. The last step in completing the cofactor is to adapt the sign reversal from element 1, 1, making the cofactor of the matrix P as shown. Finally, we can complete the first operation of determining the adjugate, and that is by taking the transpose of the cofactor. By transpose, we are just to interchange elements in rows into columns, which means elements of row 1 become the elements in column 1, and so on. After identifying adj P, we can then tackle the bar on top, which means conjugate. Taking the conjugate of adj P is simply flipping the signs of the imaginary numbers of the matrix. Thus, for adj P bar, element 1, 1 is negative 22 minus 6I, element 2, 1 is 10 minus 20I, and element 3, 1 is 38 plus 16I. From the second column, the elements become 16 plus 2y on top, followed by negative 5 plus 15I at the middle, and negative 13 plus 3I down below. The third column then contains 2 plus 12I, negative 7 plus 15I, and negative 11 minus 17I. As the operation is completed, we can take the determinant to have the final answer. With a 3 by 3 size, work on Sarri's rule. Mirror the first two columns and start by multiplying elements in the diagonals and treat them as positives. The first diagonal has elements negative 22 minus 6I, negative 5 plus 15I, and negative 11 minus 17I. They yield negative 7,300 minus 100I. The second diagonal elements are also multiplied. They are 16 plus 2y, negative 7 plus 15i, and 38 plus 16i. And their product is negative 9,012 plus 6,316i. For the third diagonal, the elements involved are 2 plus 12i, 10 minus 20i, and negative 13 plus 3i. Multiply together to have negative 3,620 minus 260i. Add all positives and arrive at negative 19,932 plus 5,956i. Solve for the negatives too. The first anti-diagonal has elements 38 plus 16i, negative 5 plus 15i, and 2 plus 12i, which provide a product of negative 6,740 minus 4,180i. The second anti-diagonal has the elements negative 13 plus 3i, negative 7 plus 15i, and negative 22 minus 6i, which when multiplied give negative 2,308 plus 4,476i. The last set of elements from the third anti-diagonal has negative 11 minus 17i, 10 minus 20i, and 16 plus 2y, resulting to negative 7,300 minus 100i when multiplied. With all negatives determined, add them to have negative 16,348 plus 196i. Then take positives minus negatives to have negative 3,584 plus 5,760i. This is the final answer.